This pack charges from 0 to full in as low as 5 minutes and still built for longevity.
5-minute charge, 100,000 cycles. Hold your applause. If this were true, physics has been wrong for a century. Donut Lab isn't selling miracles. They're selling half-truths. Wake up. I'm going to show you why this revolution isn't meant for your car. To understand why, you first need to understand what engineers call the breathing of a battery. In any true lithium-ion or solid-state battery, energy storage relies on ion intercalation. Lithium ions move in and out of the anode and cathode, forcing the active materials to expand and contract typically by 5 to 10% in volume. Now imagine inflating a balloon and then deflating it over and over again. No matter how good the material is, after a few thousand cycles, microcracks will form. Electrical pathways will break, and the battery will die. That is why even the best batteries in the world today only dare to guarantee 3,000 to 5,000 charge cycles. So, how does Donut Lab dare to claim 100,000 cycles? The answer lies in a sleight of hand, a redefinition of what a battery actually is. They are not relying on deep electrochemical reactions. To achieve that extreme durability, they are forced to use surface adsorption, the core operating principle of a capacitor. This is the trap hidden inside the Regen plot, the chart Donut Lab never wants you to see. The Regen plot describes a fundamental and unforgiving rule. You can choose either high-energy long-range or high-power fast charging, but never both. No technology can sit at the peak of both extremes at the same time. By hybridizing capacitor-like behavior into their architecture to achieve insane charge speed and cycle life, Donut Lab is implicitly admitting that the real-world energy density of the entire pack must be extremely low. Yes, in a laboratory, a single cell might show 400 watt-hours per kilogram at slow discharge rates. But once you force that cell to behave like a capacitor charging and discharging at extreme currents, energy efficiency collapses due to internal losses. Worse still, this creates a nightmare in voltage behavior. Chemical batteries maintain a relatively stable voltage around 3.7 volts, allowing smooth vehicle operation. Capacitors, by contrast, suffer from a linear voltage drop during discharge. To prevent your EV from feeling impotent, every time you press the accelerator, you would need an extremely complex and expensive inverter and DC-DC conversion system to compensate for these voltage swings. Has Donut Lab told you how much that supporting power electronic stack will cost? Or are they waiting for you to discover it? When you see the invoice, the disappointment does not stop at chemistry. It escalates into something truly terrifying. When we step into thermodynamics, where the law of IR losses becomes the executioner of fast-charging fantasies. Do not be fooled by demonstrations on a single cell. A lone cell sitting on a lab bench is easy to cool. It is surrounded by air. But an electric vehicle requires thousands of cells packed tightly together into a dense battery pack. Now do a simple calculation. To charge a 100 kilowatt-hour battery pack in 5 minutes, you need 1.2 megawatts of power. Even if Donut Lab reduces internal resistance to absurdly low levels, the square of the current thousands of amperes will still generate an enormous amount of heat, enough to turn the battery pack into a metal furnace in seconds. Cells buried deep inside the pack will have nowhere to dump that heat, creating dangerous localized hotspots. At that point, air cooling or conventional liquid cooling becomes useless. You would be forced to submerge the entire battery pack in dielectric fluid and equip it with high-power industrial pumps. But here comes the unavoidable counter question: how much does that cooling system weigh? It would erase every weight advantage solid-state batteries claim to offer. Your vehicle would be carrying a mobile refrigeration plant, transforming it into a heavy, bloated machine rather than a sleek performance EV. And then there is thermal stress. A sudden temperature rise during a 5-minute charge, thermal shock forces different materials inside the batteries to expand at different rates. This mismatch rips apart internal bonds, causing delamination after just a few hundred cycles. Has Donut Lab solved the delamination problem, or are they simply ignoring it and hoping customers never notice? The final blow, the one that completely destroys any illusion of mass market viability, comes down to a single word: manufacturing. The gap between a laboratory demo and a real factory is not a step, it is a chasm. One dirty secret of solid-state batteries that few people talk about is stack pressure. To maintain proper electrical contact, solid materials must be compressed under tens of atmospheres of pressure. In a lab, this is achieved with hydraulic clamps. But in a car, maintaining that pressure across a full-size battery pack for the vehicle's entire lifespan requires extremely thick, heavy structural frames combined with complex mechanical compression systems. How much does that steel structure weigh? It turns a theoretically high cell-level energy density into a disastrous pack-level number. You buy a light battery, only to haul around tons of steel just to keep it functioning. Then comes the manufacturing method Donut Lab proudly promotes screen printing. In reality, this is an economic bottleneck. While giants like Tesla and Panasonic use continuous roll-to-roll coding running meters per second, screen printing operates in a stop-print-move cycle. It is slow, labor-intensive, and orders of magnitude less efficient. To reach gigawatt-hour scale output, Donut Lab would need 10 times the factory space and 10 times the equipment of established players. Capital expenditure would explode, pushing battery costs into the stratosphere and killing any hope of competing with conventional lithium-ion packs. And that is before yield losses. Ceramic solid electrolytes are brittle. High-speed production easily introduces microscopic cracks. A single hairline fracture is enough to cause a short circuit and scrap the entire pack. Are they prepared to throw away 30% of production as defective? And who pays for that waste? You do. So who is this technology really for? It is for million-dollar supercars sitting in climate-controlled garages, for military drones where cost is irrelevant. But for you, the person hoping for an affordable EV that charges as fast as filling a gas tank, forget it. Donut Lab has painted a vision of paradise, but the gate to that paradise is locked behind physical and economic barriers they cannot overcome. The brutal truth is that this technology is not meant for you and likely never will be at a price you can afford. Do not be blinded by illusionary numbers. Look at the engineering reality, and you will see that miracles do not exist, only physical limits do, and they are eternal.